Hi, my name is Sophia Hii Hui Hui with metric number 101107. There are different types of scheduling algorithms, namely first come first serve, shortest job next, shortest remaining time, and round robin. Round robin is the most widely used scheduling algorithm in multitasking and real-time environments as it can sustain preemption performance effectively. It is also the most popular algorithm due to its fairness and starvation-free nature towards the processes achieved using time quantum. When time quantum is large, there is less context switching. At one extreme, a very large time quantum will cause poor response time and resembles first come first serve. Conversely, a small time quantum results in high context switching and a very small time quantum will lower the CPU efficiency. Hence, the system performance depends heavily on the size of the time quantum. In this project, we use Python to implement the round-robin process scheduling algorithm. We evaluate the job list with different time quantum, ranging from 5 to 60, based on performance metrics such as turnaround time, waiting time, and number of interruptions. Lastly, we will recommend the best time quantum based on evaluations.
Next, we will proceed to run the code with different time quantum. As shown here, this is our code using Python, which consists of job class that defines the properties of a job reader that reads job details from a CSV file and parses them into object using regex, round-robin scheduler, which is the core logic that simulates time-sliced job execution and tracks metrics, result display that display outputs metrics for individual jobs and calculate overall averages for analysis, and lastly, interactive menu that allows user to experiment with different time quantums and view results dynamically. We also include the file path, which specifies the exact location of the file. The file that we are using is a CSV file, and this is how the data looks like in the file. This enables the program to read the assigned job list which stored in other file. Without further ado, I will proceed to run the code. First, we need to choose Insert Time Quantum and enter the evaluated time quantum. The displayed output here is a table containing arrival time, burst time, interrupts, completion time, turnaround time, and waiting time for each job, and also the performance matrix that includes the average turnaround time, average waiting time, and total interrupts. Then, I will display the result for all time quantum by choosing option number 2 in the main menu. The result for all time quantum will be displayed from 5 to 60. Then, the option number 3 in the main menu is to view the summary of the performance metrics. It will show which time quantum has the lowest average turnaround time, lowest average waiting time, and the lowest total interrupts. So that's all for running the code part with different time quantum, and here is the screenshot of the calculation results of all performance metrics for every time quantum, which is 5 and 10, 15 and 20, 25 and 30, 35 and 40, 45 and 50, 55 and 60. Next, we will proceed to how to get the calculation result.
Good morning, sir. My name is Nur Alina, and I will be presenting on how to get the calculation results. In these slides, we can see there are codes for calculating turnaround time, waiting time, and number of interrupts. Firstly, we can get the turnaround time by subtracting the completion time with the arrival time of the job, while waiting time can be calculated by subtracting the turnaround time with the total burst time. Next, by adding number of interrupts with 1, it can give the values for the number of interrupts. Our next slide contains the code to get the result of the average turnaround and waiting time and also the total interrupts. To get the average of turnaround time, we need to sum all the turnaround time and divide it with the total number of jobs. And we use the same formula to calculate the average waiting time, where we just need to get the total of waiting time and divide it with the total number of jobs. Lastly, the result of total interrupt is calculated by adding each job's individual number of interrupts to a running total. That's all for my part. Thank you.
This is the comparison chart that shows the result of calculation on average turnaround time, average waiting time, and the number of interrupts in different time quantum. In this table, the lowest quantum type 5 give the highest turnaround time, which is 255,243.20, the highest average waiting time, which is 246,659.93, the largest number of interrupts, which is 51,481, while the lowest average turnaround time, which is 254,873.87, and the lowest average waiting time, which is 246,290.60, is shown by the quantum time 50, but the lowest number of interrupts, which is 4,275, is given by the quantum time 60. The difference between the highest and the lowest average turnaround time is 369.33, and for average waiting time the difference is 366.33. And last, for number of interrupts, the difference is 47,206. Compare the difference between the lowest and the highest result for each session. The relationship between the average turnaround time, average waiting time, number of interruptions, and quantum time is inversely proportional, which means the increase of quantum time will make the average turnaround time and average waiting time decrease until the suitable quantum time for the chosen job, but number of interruptions will continuously decrease.
Now, I'm going to discuss about the evaluation of results. Firstly, in terms of average turnaround time and waiting time, they will decrease as the quantum time increases. This is because larger quantum times reduce the frequency of context switches, which results in minimizing overhead and improving overall efficiency. For example, with a quantum time of 5, average turnaround time and waiting time is the highest. However, at a quantum time of 50, these metrics drop to the lowest. Secondly, in terms of number of interrupts, it will decrease with increasing quantum time. A shorter quantum time may cause more frequent preemptions and context switches, resulting in higher number of interruptions. For example, at a quantum time of 5, the number of interruptions is the highest, whereas at a quantum time of 60, it drops to the lowest. This decrease highlights the trade-off. While shorter time quantum improves responsiveness, they incur higher context switching overhead. Next, in terms of excessive size of time quantum, a very large quantum times leads to poor responsiveness for interactive processes. On the contrary, a very small quantum time results in excessive interruptions, negatively affecting performance despite improved responsiveness.
Next, I will discuss justification and recommendation based on this project. As we know, the performance of the round-robin scheduling algorithm mainly depends on the size of quantum time. The time quantum should not be too big or too small. Based on our project, the recommended time quantum to complete the job list given is 50. At time quantum of 50, the algorithm strikes a balance by achieving low average turnaround time and average waiting time, while keeping the interruptions relatively low. This configuration ensures efficient CPU utilization, improves throughput, and a balanced level of context switching overhead. Overall, the best time quantum to be recommended to the client is 50, as it aligns with the goals of maximizing efficiency and minimizing delays. In conclusion, round-robin algorithm for process scheduling is a widely used approach to ensure that processes in operating systems get equal and ample opportunities for their execution. However, its effectiveness highly depends on the choice of time quantum. Based on our analysis, the optimal time quantum is 50. Smaller time quantum results in higher average turnaround and waiting time due to frequent context switching and increased interruptions. Meanwhile, larger time quantum slow down system responsiveness by increasing both turnaround and waiting time, but with minimized interruptions. Obviously, an appropriate and suitable time quantum for round-robin scheduling is dominant for system performance and effectiveness. That's all. Thank you.